Cosmology, the study of the entire universe, the ever-vast expanse that we unfortunately live in.
I mean, it's just like so huge, you know?
Yeah, there's definitely some stuff in there.
It's the universe. I don't know what you want me to say.
There's so much that humans don't understand about it, and yet so much that they do. Despite how much that we don't know about the universe, there are definitive structures that we can observe and classify, usually based on the size, from the tiniest subatomic particles to the largest filaments of galaxies. We know that an atom is made up of subatomic particles, protons, neutrons, and electrons. Atoms come together to form stars, and these stars form galaxies, and those galaxies form clusters, and those clusters form superclusters. And on this scale, we can identify voids, filaments, and sheets, all of which are structures that are in our universe. We may be able to identify and define these colossal structures, but how do we measure them? Where are they found? To figure this out, we need to understand a fundamental principle, a cosmological principle, if you will. Observations have discovered that the universe is uniform throughout in all directions, just like a smoothie.
The universe is like a smoothie because it's both homogeneous and isotropic. This means that every 300 megaparsec cube is just like any other.
We know this because of galaxy surveys, which look like this, and they show the distribution of galaxies up to 1,000 megaparsecs away within 12 degrees of the celestial equator. With this, we can observe voids, filaments, and walls, the most famous of which being the Sloan Great Wall. Pencil beam surveys also help us measure the distribution of galaxies. They take a small area of space from north and south celestial poles and plot it on a graph. Pencil beam surveys also let us observe voids and walls.
I mean, why would you call it a pencil beam survey? A pencil's already a beam. Just call it a pencil survey. Or just call it a beam survey. Why do you compare it to a pencil? Who comes up with these names?
With these pencil beam surveys, we know for a fact that the universe is both isotropic and homogeneous, but there's something amiss.
Assuming the cosmological principle were true, we would expect the night sky to be as bright as the sun. But this is not true, and so here we have Olber's paradox. But we know that the universe is both homogeneous and isotropic, so we either assume two things, that the universe evolves, or the universe is not infinitely expanding.
Astronomers have been asking which of these two theories is true, and the answer is kind of both. We know that every galaxy appears to be moving away from us from Hubble's clock, and so we can determine how fast an object is moving and also how far away it is, and therefore we know the age of the universe of 14 billion years. We can also hypothesize that all matter and energy originated from one single point. This point is known as a primeval fireball, and it was only a matter of time before it exploded into the cold, dark, lonely universe that we all know and hate. This event is known as the Big Bang.
Where did the Big Bang happen? Nowhere? Everywhere? Nowhere and everywhere at the same time? I mean, yeah, it happened at a single point, but
If we microwave a marshmallow, we can see it expand, just like the way the universe does. So if you mark a point on the universe, it will appear to expand forever. So no matter what point you pick, it always looks the same. So the Big Bang truly could have happened anywhere. Well, in fact, it did happen everywhere. Will the universe expand forever? Or are our days numbered? To answer this question, we need to look at critical density. Critical density is how much density is needed to allow gravity alone to stop the expansion of the universe. We know it to be approximately 5 hydrogen atoms per cubic meter, which is an extremely low density. So if the density of the universe is above that, expansion would halt and eventually start to contract. The second option is that the universe expands forever, so eventually we would see no stars or galaxies in the night sky, and our own galaxy would dissipate into nothing, into something what astronomers call a cold death. The next question astronomers have asked is what shape the universe is. The most common belief about the shape of the universe is that it is a sphere that's just constantly expanding. But this would only be possible in a high-density universe, or a density where its density is greater than the critical density. If the density is lower than the critical density, then the universe would be an open universe, which would be shaped kind of like a Pringle. If the density is equal to the critical density, then we have a critical universe, which would be flat, or at least flat. So we know the size of the universe, what shape it is, but what's it made out of?
We obviously know about all the different elements on the periodic table, and like that's all the physical matter that we know of. But there is something else out there that's responsible for the expansion of the universe. And because we don't really know what it is, we've coined the term dark energy to describe it.
I mean, like, we don't even know what it is, so even if I wanted to explain that, which I don't, I couldn't. So, what do you want? Is this? Is that what you want? Leave me alone.
In 1964, it was discovered that there is a constant quote-unquote noise in the universe, which provides evidence for the Big Bang.
This constant noise is known as cosmic microwave background, and it's radiation that happened during the Big Bang.
As of right now, most of the density of the universe is made up of dark energy, followed by mass and very little of radiation. This composition has not always been the case, however. A little over 4 billion years ago, the universe was matter-dominated. Even earlier, there was a point where radiation dominated the universe, which happened between the Big Bang and 50,000 years after it. This radiation era is very crucial to understanding how the universe came to be. Radiation could actually be turned into matter through a process called pair production.
You have two gamma rays that collide to form a positron and an electron, which are known as a particle-antiparticle pair. This process was in equilibrium until it wasn't, when the temperature was too low for it to happen anymore. So, all matter in the universe today was created from radiation.
4 main fundamental forces guide all matter in the universe: the strong nuclear force, weak nuclear force, electromagnetism, and gravity. It is theorized that from the Big Bang to very, very, very shortly after, these forces were indistinguishable from one another. Now, at one point in time, we thought that these forces were unified in what we call grand unified theories. This is the idea that there was one superforce made up of the 4 fundamental forces that we've already talked about. However, these forces did split away from each other eventually. Now, in quantum mechanics, any particle that transfers one type of force to another particle is called a boson.
We can actually compare the transfer energy from one particle to the next to again catch. Imagine my hand is a particle and this ball is a boson. Now if I throw the ball,
After this very brief gut epoch came the quark epoch, which is where we start forming heavier particles, such as protons and neutrons, which is where we begin the formation of matter.
It's also important to know, like, how little time this actually took, you know? Like, less than a blink is how long, like, this whole thing went. Like, that's crazy. Like, less than that. Are you kidding me? That's, dude, like, that's...
As the universe got cooler, neutrons and protons started fusing, forming hydrogen and helium, the first atoms.
so because I'm made up of elements which are made up of quarks, by definition I am a quarked up white boy. I've been planning that all video.
Here are the main epochs in cosmic history. I don't feel like explaining them because I'm already like 3 minutes over time, but
You could say that's pretty epic.
even though all these processes are explained by the Big Bang, the theory itself still has problems of its own.
If you look at two opposite points in the distant universe, the cosmic background radiation was observed to be the same. However, the Big Bang theory tells us that those areas are too far away from each other to interact with each other with the time it took the Big Bang to actually happen. This is called the horizon problem.
Yeah, we don't really have an explanation for this. Oh well.
Another problem we have with this is the flatness problem, which is the idea that there shouldn't really be a reason why the density of the universe is as close to the critical density as it is. Why isn't the density 1,000,000 times greater, or 1,000,000,000 times greater, or 1,000 times smaller? You get the point.
Yeah, we don't really know that either.
As we continue talking about the universe, things get a little hairy. Remember all that stuff about gut and Planck epochs? Those are only explainable through quantum physics, part of which includes the existence of scalar fields. These fields help determine the properties of particles, whatever that means.
What's interesting about these fields is that some of them are in higher energy states, which gives them energy to empty space and what we call vacuum energy. And this energy is the reason as to why the universe expanded at a higher rate early on in what's called the epoch of inflation.
Because the universe fluctuates in density, inhomogeneities or deviations from perfect density can be observed.
I mean, do we really have to go over this? Okay, fine. Normal matter cannot be solely responsible for the concept of inhomogeneity throughout the universe, so we look to dark matter to explain it. Oh, we've heard that before, looking to dark matter to explain things. So sick of it, dude. We don't know anything. Can I just show a diagram? Okay, so we can classify dark matter into two types, either hot or cold dark matter. Hot dark matter is made up of lighter particles such as neutrinos, and cold dark matter is made up of, well, we don't really know what it's made up of. We don't know anything. Ever, at all. The universe? How do we know it's there? We don't. I'm done with this, dude.
We can observe fluctuations in temperature in the microwave background. Here we have the Kobe map of the sky. We can see clear differences in temperature and therefore density. These regions are found to be in line with locations of voids, filaments, and galaxy clusters.
Well, that's about it. I mean, there's more to talk about, but I really don't want to, so. See ya.